Welcome everyone to today's Keeping Current. Today we have some homegrown talks. We have first Professor Brent Harrison, who will tell us everything about deep learning, or about machine learning. Take it away.
Yes, actually telling very little about deep learning because you can't give it all away for free. All right, so hi everyone. My name is Brent Harrison, and today I'm going to attempt to accomplish the ambitious goal of giving the overview of machine learning in 30 minutes with a presentation that I have lovingly titled Drawing Lines for Fun and Profit, or a gentle overview of machine learning. So let's start at the beginning, shall we? It is, I think, a gross understatement to say that machine learning is very, very popular and very, very hot right now. It is not hard to go online and find a bunch of examples of these really cool and really, really sweet looking ML systems that do all of these neat and complex things. But that being said, it can be really difficult, ironically, to tease apart what exactly machine learning is from all of these examples. And so that's why, and a lot of the things that I'm going to go over today are things that I talk about in a lot more detail in my class, Pitch for 460. The first place that we start is with trying to nail down what this definition is. And so I always like to, in a tongue-in-cheek way, bring up this XKCD comic because it kind of, I think, hits at, maybe scathingly so, the core of machine learning. It's just a big ball of linear algebra that you throw data into and then get stuff out on the other side. Yes and no, maybe not super useful to think of things that way, but surprisingly accurate in some cases. But no, I have over the years come up with what I find to be a more useful definition for launching off. And I've kind of built this definition after looking at all of the many definitions that you can find online when you search for what is machine learning. And so I like this one, but it is not the only one out there. And if you've taken my class, this should look very, very familiar. So machine learning systems are those that can automatically improve their performance based on experience. It's very, very vague, but I kind of like it that way. And the reason that I like it that way is because it is general enough to describe most of the very complex, very varied machine learning methods that you'll find out there today. And even though it is vague, you can still start to pick out certain requirements by breaking this apart. Laser pointer go. So first off, machine learning systems are those that can automatically, so right away we get something. These systems need the ability to do stuff on their own. I, as the creator, am not going to be giving it a bunch of rules to follow. It should be able to, learn for itself. So it can automatically improve their performance. So we've got something else now. There needs to be this notion of a performance metric. So it's going to need to be able to identify for itself automatically whenever it's done something right or done something wrong. And then finally, based on experience. So what this means is that either it's going to need to be able to kind of act in the world to generate some set of experience for it to learn on, or we're going to give it a bunch of data that it can kind of use as a proxy or a bootstrap for experience. So yeah, I like this definition, cool stuff that you can get out of it. And that's kind of how I see machine learning. Now let's get into some more specifics. Oh, and feel free to stop me at any time with questions. So a machine learning system, it relies on data. Any kind of system or machine learning system that you run into, there's going to be data involved somewhere. In this talk, we're going to primarily focus on data that looks kind of like this. So what are you looking at? The terminology that I typically use is you're looking at a set of examples. Examples of what? Examples of anything. Depends on the problem. Here, this is specifically a data set that is used, it's kind of a toy, that's used to train a system to predict whether someone is going to cheat on their taxes, because this is all you need. So each row in this data set represents a person. Each column represents a set of features describing said person. So in this case, in this example, person 1 would be described by whether they got a tax refund. In this case, they did. Their marital status. In this case, they're single, and their taxable income. 125K, sure. These features can take on different data types. So one is categorical, or 2 are categorical, 1 is continuous. And a lot of, like, there's no requirement on what your data has to look like, but oftentimes what it looks like will determine the type of method that you use. Let's see here. Yeah. So the goal of a machine learning system at a high level is to take this data and, well, to learn something from it. Like what it's learning largely depends on the task and the model that you use. But ideally, you're looking to learn generalizable knowledge. Boop. And so what do I mean by generalizable? Oh, yes?
Here it looks like married people don't cheat.
On their taxes.
Okay, all right. Good.
Only on their taxes. So what do we mean by generalizable knowledge? So ideally, you should be able to take an unknown example, an unknown data point, and use the things that you've learned from these known data points on this unknown one. You should be able to take the knowledge that you've gained and apply it to the great unknown. Now, how do you do that? How exactly does a machine learning system go about learning this generalizable knowledge? And that brings us back to the crux of the talk, the topic of the talk, which is drawing lines. So I like to think that all machine learning is just a very fancy way to draw lines that describe your data set. Because if you can describe your data set, it turns out most of the time, well, what you hope is that that is that generalizable knowledge that you're looking for. In particular, we're going to focus on 2 kinds of lines, specifically lines of discrimination and lines of regression, lines of fit. These 2 lines correspond to by far the most common tasks in machine learning, classification and regression, respectively. So in a classification task, what you're doing is you're trying to come up with a line that separates your data set based on some value. In this simple example, those values are pluses and minuses. So you can describe this data set using a single line if that line separates it. And if you were to get in a new data point, even if you didn't know if that data point was a plus or a 0, you could give it a label based on what side of the line it's on. Classification. Regression, so drawing lines of fit, is the second type of task that you typically see in a machine learner, the second most common one, I would say. Like this isn't an exhaustive list of machine learning tasks, but these are by far the most common. And so a regression problem typically involves drawing a line that describes your data set by minimizing the distance between each data point and the line itself. And so here you could describe an unknown example. So like assume or pretend that you got in a data point, you knew its X value. Well, you could use this line to come up with a Y value and hence make a prediction and thus generalize this knowledge gained from known examples to unknown examples. So those are the tasks that we're going to talk about for machine learning. So next, let's talk a little bit about methods. So there are 2 general methods or paradigms in machine learning that largely have to do with what type of data you're learning from. And those are supervised learning methods and unsupervised learning methods. Some of you, especially those of you who have taken my class, might be screaming, oh, but what about reinforcement learning? We're not going to talk about that in this talk. We're going to focus on these because these are, again, the most common ones. Although, yeah, they're the most common ones for right now. So let's start with the most straightforward of these, supervised learning. So conceptually, supervised learning is the easier of the two to understand. And really from a learning perspective, it's also the easier of the two to understand. So I mentioned that the big difference between these two, supervised and unsupervised learning, has to do with the type of data that you have available. In supervised learning, you're dealing with something called labeled data. Now, what is labeled data? Well, it's just data that comes with an extra piece of information that tells you or gives you an idea of what you're supposed to do. So an example of labeled data might be a set of images that have a label describing what's in that image. This is actually really bad examples because these are really bad labels. A better example, although maybe a slightly drier one, is something like this. So this is a data or part of a data set from the UCI repository, dataset repository. And this is a data set about predicting the quality of wines. So here, each example represents a specific wine, and each column is a feature describing that wine. So citric acid, residual sugar, things like that. And your job, the class label that comes with this data set, is quality. And so having this class label gives us a lot of stuff that makes, in a way, our job easier, because it tells us, oh, this is what I want my machine learner to do. I want it to take in all of this wine information and predict this class label, this quality. So one way to say this is that it gives us a clear goal of what we want our system to do. And in addition to that, in some cases, it can let us know when we're doing a bad job or a good job. Do we predict that class label or not? And sometimes, if that class label happens to be numeric, it can tell you how bad you've messed up. So if I were to predict, for example, a 1 when I should have predicted a 7, that's probably going to be much worse than if I had predicted a 5 when I was supposed to predict a 7. So supervised learning is from that perspective, straightforward. So now let's talk about some methods. So how do we do this? What are some examples of supervised learners? And we're going to start with where I started my class, which is the decision tree, a classic. And we start with the decision tree because, I don't know, I feel it is one of the best examples of a classifier. So we're trying to discriminate our data. It's also one of the simplest machine learning methods to use. So if I had a tree, if I had a decision, well, first off, let's talk about what exactly the decision tree is. So like every tree structure, we have nodes, we have edges between those nodes, and we have leaf nodes. So the nodes in this case represent features in our data set. So in this example, I have at least 3 features, one of which is called weather, one of which is called time, one of which is called hungry. Edges between those nodes represent values that that feature can take on. So in this case, the weather can be sunny, cloudy, or rainy. And the leaf values in this tree represent the class labels that I've seen. So I can predict that you take the bus, I can predict that you walk somewhere. So elements of the tree are based on what my data looks like. And that's a pretty common theme amongst all of these methods that we're going to talk about today. So using this tree is very simple. If you're given some unknown example and you want to use this model to make a prediction, you simply, well, start at the root and you look at the feature that's associated with the root. In this case, it's weather. And you just start traversing the tree. So I go and I look at my example. I look at weather and I say, okay, is it sunny, cloudy, or rainy? If it's, let's say it's cloudy. Okay, well, I then traverse down to the next node. It says hungry. So in this example, I'll go now look at hungry. look at its value, and if it's, let's say it's yes, hey, I'm done. I can make a prediction at this point. I think you should walk. So even if I've never seen this example before, this model can come up with a prediction based on what these feature values are. All right, now, what exactly is going on when you're training? So when you're training these models, what you're really doing is you're constructing the tree. And in particular, you're answering a very simple question. What feature do I make the root? And what feature do I make the root of the tree? And what feature do I make the root of every subsequent subtree? And in fact, if you look at the pseudocode, it's essentially just a recursive walk of this, picking out features to put as roots of various subtrees. And how you choose that is you typically have some statistical measure of purity, of how well this feature can predict various outcomes. So in this case, weather is chosen as the root because if weather is rain, in the training set, it's seen that overwhelmingly, those have a class label of bus. And so this splits the data up really well. So I'm going to start here. And then as you go along, you just subdivide the data until you end up with a full tree. Now, one of the things that I want to do with this is a talk about drawing lines. I really want to try to visualize what these decision boundaries look like what exactly you're making when you make this tree or use any of these models. And so this is not for the tree I just used here, but this is a decision boundary for a decision tree. One of the reasons that I love decision trees so much is that they can make very, very complex boundaries with very, very conceptually simple, trees. Like using them is very simple, but they can make really, really interesting boundaries. So it's a nonlinear classifier. And yeah, this is just an example of what one of these looks like. So as you can see, it divides up the space and it's based off of those feature values. So those are decision trees. I've talked about those enough. So that's a classic example of a classifier. And now what I want to do is give you a classic example of a regressor, a regression model. And what's more classic than linear regression? One of the things to note about a decision tree is that it kind of obfuscates how you translate the tree itself into a decision boundary. You don't have that with linear regression, as you're going to take direct control of the model itself. So the line that you're learning to draw in a linear regressor, in this case, it would be this straight line. What does that look like in practice? Well, it looks like this function that we should all be somewhat familiar with. I forget which middle school class we went over this in, but the old y equals mx plus b. This is a more general version of that formula, and it's in a more like stats language, but it's still the same thing. So the idea here is that our model, the line that we're learning to draw, is this linear combination of feature values that are weighted by some set of learnable weights, trainable weights. So here, y, the dependent variable, this is the value you're going to predict. This is your class label, or your prediction of your model. x1, x2, xn, all of these are your input features. Here, doop, doop, doop. B0, your intercept, also known as a bias term. This is one of your learnable weights. B1, B2, all the way to Bn, coefficients. This is what you learn. So whenever you're training a linear regressor, you're actually picking out some set of weights that's associated with this line that you're drawing. And how you pick out those weights, well, there are a lot of different ways to do it. In fact, with linear regression, there are some nice analytical ways that you can do this. But I thought this would be a nice time to talk about gradient descent a little bit. So it turns out with each set of weights, with each specific set of weights that you assign, you have an associated error. Because we have a supervision signal, because we have this class label, we can directly calculate error. as you change those weights around, you end up with a different error. And so you can actually map that error function as something that looks kind of like what you've got on the left here, in the best case, a nice little convex function. And if you find yourself in that situation, you can actually use that error value. You can use this function to determine the direction and magnitude to update your weight values. Such that you move down this error gradient and eventually end up at a minimum. And so as you move down this error function, as you see in the right side of things, you update your model such that it minimizes the error. And so this is a common way to do linear regression, gradient descent. Okay, doing good. So next, by far the most popular method out there today, and by far, I'd say the most popular method when I teach this class, neural networks. So neural networks I see as kind of an extension of linear regression, but in a much more complicated way. So what is a neural network? So the basis of a neural network are these things, these computational units called neurons. In this graph, these are the nodes of your graph. They are organized into layers. In this neural network, we have three layers, an input, one hidden layer, and an output layer. And each layer is fully connected to the next one with weight values. To understand how a neural network works, it's important to understand what's going on inside the neuron. And it turns out that every neuron functions pretty much the same way. There's room for variation, but they're pretty much always going to take in some weighted combination of your inputs. Hey, these are the weight values that we saw in the network. So they take in some weighted sum, a weighted average, however you want to refer to it. And this value is passed into some nonlinear activation function to produce some output. Here are some example nonlinear activation functions. I won't go into a whole lot of detail on these. I just kind of want to put them on the screen so that you can see them. Which one you pick, it's problem dependent. But these are all valid options. So what happens, like how you use this system, or how you use a neural net, is you take in your input, you pass it through each layer, generating output. You run it through the neuron, you calculate the weighted combination of inputs, you run it through your activation function, and that'll get you the output at the next layer. And then you just repeat this process until finally you've got your final output. While learning this, what you're doing is, much like in linear regression, learning a set of weights. And you're even using a process that's very similar to gradient descent, only updated a little bit in order to deal with the complexities introduced by this kind of this graphical model here, this layer-based model, which is why I consider this an extension of gradient descent. Now, what I think is really interesting is what goes on inside of those neurons. So there's been a lot of interest lately in understanding like what exactly a neural net learns, and in many cases we can't quite figure it out, but in some cases we can, and this is one of those cases. So here we have a very simple neural network. We've got two hidden layers, and we get to actually visualize what each neuron is learning. And here, what we're seeing is that each individual interior neuron is learning, well, how to draw a line, a very simple line to start off with. And then something really, really cool happens at the later layers. All of these things are combined together in order for these later neurons to learn more complex decision boundaries. So here we have these were combined in two different ways to learn two different decision boundaries. And then finally, at the last layer, these were themselves combined together to learn the last one. And so one way of thinking about neural nets is they build up more and more complex, lines as you go along. Really, really neat. And thus I stop with supervised learning. And now I've got 6 minutes. We're going to cover all of unsupervised learning in 6 minutes. So the biggest difference between supervised and unsupervised learning is you now no longer have a class label, which doesn't sound like it would be problematic, but it ends up being a really big problem, mainly because we lose that clear goal that we're trying to work towards. Without a class label, there's all kinds of tasks that we could actually perform. The task that I'm going to talk about here is one of the more common ones, and that's clustering. So by far, like the first clustering method everyone learns is k-means. So k-means is a partitioning cluster method, which means that you're trying to divide your data up into groups, into similar groups. And so you can even see here in this example, the line that it's drawing is this fun Y shape. All machine learning is drawing lines. And so how it works is it works by assigning these things called centroids. In this example, the red centroid is a cross, the blue centroid is a circle, the yellow centroid is an X. And what it does is it will iteratively update these centroids based on my data. So we start off with some random assignment, this random placement of centroids, and then you're going to look at, okay, what are the points closest to each centroid? Assign those to a cluster. Well, in assigning those points, what you've done is forced the centroid to update, because now my average value, data value is different. So you move the centroid, which is going to cause you to update your decision boundary and potentially have new points. So you reassign points and you just repeat this back and forth and back and forth and back and forth until you finally converge. And this happens here at around around now. But this is not the only way. One of the other problems with unsupervised learning is that you don't necessarily have good goal metrics. And so with clustering, we often use heuristics to evaluate the quality of a clustering. And two of those heuristics are intra-cluster distance, how close points in the same cluster are, and inter-cluster distance, so how far away points in other clusters are. So a good clustering would be one that has low intra-cluster distance, so tightly packed clusters, but high inter-cluster distance, very distant clusters. Another interesting way to do clustering is this class of technique called density-based clustering. One of the problems with k-means is that the clusters learned there are spherical, and it turns out all data is not spherical, or data is not always spherical. And so what density-based clustering tries to do is build up clusters by looking at, looking for areas of high density, points that are closely packed together, separated by areas of sparsity, data points that aren't closely packed together. And what that results in, and you can see here, clusters get built out and they kind of radiate out until it finds runs out of other points to jump to. And so that is, we'll go fast. That is density-based clustering. This was mainly just meant to drive home the point that there are many, 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 many ways that you can build clusters, and they each have their own way of separating data out. And some are more applicable on certain types of data than others. So I've gone over two. There are way many more out there. And that is unsupervised learning. So now I feel that it is necessary to at least make a head nod towards deep learning, given its popularity. And so I want to, this is mainly more a preview for another talk that might give this semester. So one of the things that we never talked about is where your features come from. Features play an important role in machine learning, but how do you learn them? And traditionally, what happened was you got a domain expert or somebody who was an expert in machine learning, or maybe you just came up with those features. And it was very time consuming, it was a hassle, and you never knew if your features were good. Well, what if the machine learner could do that for you? What if your neural network could perform feature extraction for you? And that's essentially what's going on with deep learning. This is one of the reasons why it's such a big deal, because it took the arduous task of feature extraction and automated it. And not just automated it, it did it in such a way that the neural network or whatever you're using is learning features that are relevant to it. And so this is just an example of here, the input to this neural network was an 8. And as you move up the convolutional layers, it's extracting more and more abstract features until the point where we just get essentially activation maps, not human recognizable, but machine interpretable. And by the time we get to these top layers, and these top layers are just feed forward neural nets like we looked at earlier, the input to these systems, or the input to this part of the network, are those features that were extracted earlier. And so that's, I think, the coolest thing about deep learning, and that's why it's significant. But of course, it would take another 30 minutes for me to go over all of deep learning, and so I will save that for next time for the talk that I've decided to call the lovingly the late afternoon double feature learning show by RKO, or a soothing introduction to deep learning. The end.
Well, you managed to fit it into 30 minutes. That's
30
great.
minutes.
Well done. And I'm sure there are going to be questions, and you will have to take them offline.
Yes.
Very, very carefully arranged, so that's the case. And thank you. I understand that a lot better than I did before.
Well,
Now I
hope
just
so.
want to see all those algorithms. But for another time.
Another time.
Very good.